or private information. All right, so this is ultimately our goal. And what they have at their disposal, Alice and Bob, they have local encoding and decoding channels, and they can also make use of this channel multiple times. And we want to know in this scenario what is the highest rate of either classical, quantum, or private information. Okay, so I said that they're connected by some quantum channels, so what is that exactly? So what does that mean? And so that's going to be one of the main focus of today's class, and hopefully by the end we'll be able to describe probably the two most important communication protocols, which is quantum teleportation and also quantum superdense coding. Okay, so let's start by going through what a quantum channel actually is, so in a more mathematical sense. So depending on who you ask, a quantum channel could mean different things to different people. So I would say that at the most basic level, a quantum channel, if you ask a physicist, is simply something that describes the physical evolution of a system. So from a physics point of view, and this is a system that's described by quantum mechanics. Right? So at a basic level, this is what it is. And we know from our basic quantum mechanics classes how we model or how we describe the evolution of a physical system. Right? And this is by the Schrödinger equation. Yeah. There's another way to think about a quantum channel, which is a more information theoretic style, which is basically what we're looking at here, which is information transmission. So a quantum channel is some medium through which you transmit information. So this could be a fiber optic cable, or it could be signals sent even just to free space. So like radio waves or something like that. So yeah. And finally, so some of the examples that we'll look at of what is a quantum channel doesn't strictly speaking fall into either, as an evolution of a system or information transmission as we traditionally think about it, but we just think about a quantum channel as some map. So it is just some map that takes states to states. So this is a more mathematical view, and it's some map taking states, quantum states to quantum states, and we just view these as like tools to help us do calculations. All right, but at the most basic level, because we are, ultimately doing physics here, we start with the Schrödinger equation as our basic step. All right, so pressure's gone there. It's fine. So, all right, so let's recall what the Schrödinger equation is. So. All right, so we probably recall from our basic quantum mechanics classes. So this is the state of some system at time t. This is given by this equation, where here h is the Hamiltonian of our system. And here we have pure state evolution. Right? So this is essentially the governing equation of any physical system from quantum mechanics, basic quantum mechanics that we see in our first course. So this is for pure states. We can also write down a corresponding equation when the state of the system is mixed. So recall that a mixed state is described by a density operator. And in general, we can view it as being a mixture, a classical mixture, probabilistic mixture of pure states. So we can view these are the probabilities that these states are prepared, but we don't have knowledge of which state was actually prepared. So the state of the system, from our point of view, is described by this type of object, a density operator. And if we sort of take the time derivative of this and use the Schrodinger equation, then we arrive at what is called the von Neumann equation. So the state as a density operator at time t is given by this. And sometimes we call this the von Neumann equation. Okay, so these are our governing equations for any quantum system. Now, the general solution to this corresponds to what's called unitary dynamics. So it is simplest to write this in the case when the Hamiltonian is time independent. So maybe you recall that in the case that our Hamiltonian is time independent, then the state at time t can be written as this. Where this is a unitary, and in particular, if H is time independent, then it's this. So this is a unitary in the sense that U is the identity, and the other way it works as well. So it's also that also holds. Okay, so this is what we have in general. Now, what we want to do now is imagine that we have some quantum system, and in general, it could be correlated with its environment. So we have a state of some system at time t0, or we can imagine that we have a joint state of the system and the environment. And the initial state of the system, let's say, is a pure state. And let's say the environment is also in a pure state in this form. Okay? Now, what's going to happen is, according to the Schrodinger equation, both the system and the environment will evolve under unitary dynamics. Okay? So at time t, we'll evolve according to this unitary. So all right, but now, because the environment is inaccessible to us, what we have to do is trace it out. So if you recall from last time, We talked about the partial trace, which corresponds to like if you have if you have a bipartite system with two systems, then in order to describe just the state of one of the systems, you trace out the other one. So the environment is inaccessible, so we just trace it out. So finally, the state of the system is given by this. And what we usually do now, so this is essentially a general form of a quantum channel. So we have some unitary, and we have it evolving this system with its environment, and then we trace out the environment. And that's it. And what we usually do is we denote this symbolically by some n acting on the input state. All right? And this n is supposed to just be some map that stands for noise. Okay, so we have this general picture. So we could call this like the Schrodinger picture of quantum channels. All right, but now, see, the thing is here, what we would like to be able to do is describe the evolution of our system by not necessarily having to think about it as some kind of interaction with its environment followed by tracing out the environment. We would like to be able to describe the action of this map in some way that its action is described only on things acting on the system of interest alone. Okay, and so this will lead us to our next sort of way of looking at a quantum channel. Okay, so the way we can do this is by decomposing this unitary. So in essence, what we'll do now is we will actually evaluate that partial trace and see what happens. Okay, so we can take our unitary and we can decompose it in this way. So okay, so these are k and j, the comma. So these are operators that are acting only on the system, and this is just a way to decompose it such that it's kind of like a block diagonal decomposition. Okay, so we can think of the unitary as being like this in some sense. It's like u00, 0, 1, and so on. All right, where each of these are not numbers, but they're actually matrices. Okay? So if we do this and we plug it in, we can basically simplify it. All right, so because the partial trace is linear, we can bring it inside the sum when we bring it out. So we will get, so it's going to be u, you have k prime, j prime. Okay? So this just follows by plugging this in into that formula for the partial trace and basically bringing the sum out, or taking the partial trace in, because the partial trace is linear. All right, so now what do we have here? So here we're going to have, because these are an orthonormal basis, here we'll get a delta, and here also we'll get a Kronecker delta. So ultimately, what we'll get is this. Right? Because the j's will be equal to 0, j and j prime will be equal to 0. And then when we trace out on the e side, what we'll get is basically a k and k prime, like this, which will be equal to that. So this is what we'll get. And now this is some action on the initial state of the system that doesn't involve tensoring with some environment state, evolving it jointly, and then tracing out the environment. Right? So this is just some action on the system alone. Okay, and let's see another property that these operators have. Because U is a unitary, what we end up getting, and this is something that can be shown. So probably I can write these summations as this way. So here, D sub E is the dimension of the environment. And we just assume that it's some arbitrary finite dimension. And so it satisfies this. Okay? So what we have basically shown is any map that can be written in this form also has a representation where the action, so now I'll just write it for a generic density operator instead of just a pure state. Has this form. Okay, so up here, we saw one representation, which I called the Schrodinger picture, or the Schrodinger representation of a quantum channel. And what we have here is what people call a Krauss representation. And we call these operators the Krauss operators. Okay? All right. So basically, this is what we call a quantum channel. So anything that can be written in this form, we call it a quantum channel. Either in this form or this form, they're equivalent. Right? So let's see, there are two important properties that maps of this form satisfy. Okay, so one, which is relatively simple, is trace preserving. So I'll call it trace preservation. Right? Because what do we want? So we started with some state initially, we evolve it, and what we have at the end of that evolution should also be a quantum state. Right? So it should be a quantum state in the sense that, if you remember from before, it should have trace equal to 1, and it should be Hermitian and positive semi-definite. Right? So anything that evolves under a quantum channel, the final state should also have these two properties. Right? And so if we take the trace of this, so let's do that. So if we take the trace of this, then we can bring the trace inside the sum. Okay, and then and now I bring the sum back inside. right? But we showed here that this particular sum is equal to the identity, right? So this is rho, which is equal to 1 if you have a quantum state. So what this is telling us is that the thing that we get after the action of the channel has the same trace as what it was initially, right? So what this means is that the map is trace preserving. So that's what that means. So okay. And the second property, which is maybe not as obvious, is this fact. So we have that what we get at the end is also positive semi-definite, in the sense that because this is positive semi-definite, it is possible to show that each one of these operators in the sum is positive semi-definite, and so the sum is also positive semi-definite, right? But we actually have something that's more than that. So we not only have that it's positive semi-definite, but if initially you start with a bipartite state instead, so you start with some rho Ra, and you send only one of these systems through the quantum channel, right? So only one of them and not the other one. So mathematically, we would write it as follows. So we would write like this. So it's identity, so it's nothing happening, so we just call it identity on the R system, and the quantum channel N acting from A to B. Okay? Sometimes we will actually abbreviate this and just write like this. Okay, so this is the same, it's just a notation. All right? We actually have this, it's greater than or equal to 0, positive semi-definite. For all bipartite states, right? And the dimension of R can be arbitrary, okay? All right, and this property is called complete positivity. Okay, so the complete part means that I can tensor with any arbitrary sized reference system and still have something that is a positive map. Okay, so we call this completely positive. Okay, so we have trace preservation and we have complete positivity. So sometimes if you're reading some paper or if you're reading a book or something like that, people will just say a quantum channel is what's called a CPTP map. So people will just say that, and this is what they mean. So standing for completely positive, trace preserving. Okay, but the way I've presented it here, it kind of the idea was to show that it kind of follows naturally if we just assume that we have the Schrodinger equation from basic quantum mechanics. So these CPTP sort of properties follow immediately if we just take the Schrodinger equation as our axiom, in a sense, of evolution of a system. Okay? Good. Is this okay so far? Yeah? Okay. All right, so we presented two equivalent representations of a quantum channel. One was the Schrodinger picture, where we have an interaction with an environment and we trace it out. We have the cross representation, and there's one more representation which I'll show. So, which is also very useful. So this is the Choi representation. Okay. So let's say we have, the following maximally entangled state. Okay, And here, the dimension of R is actually equal to the dimension of A. So the dimension of A is, or yeah, A and R is equal to D, which is also the input dimension of the channel. Then so this is by definition. So this is the Choi representation is a state that we get by sending the A part of the channel. Sending the A part of this system, of this bipartite state, through the channel. So and sometimes we will not have this normalization factor here. So we often write this as the gamma vector. So this gamma vector is just the maximally entangled state vector that we have here, but without the normalization factor, right? So sometimes we will write this as 1 over D. So let me actually expand. Let me expand this and see what it looks, so we can see what it looks like. So all right. So now, based on this, we can actually see why this representation is useful, because objects of this form, with k and k prime like this, they actually form an orthonormal basis in the operator space, right? So this is an orthonormal basis for all operators acting on this Hilbert space of system A. So what this means is that the Choi representation in just one matrix can give us the action of this quantum channel on any on all of the basis vectors, or on all of the basis elements. So that's one way in which this is useful. Okay, so we can also write it like this. So this is just some other notation where it's just this, but without the normalization factor. So okay. Now, because this gives us the action of the channel on all of the basis elements sort of at once, right? So because it does that, we can actually represent the action of the channel in terms of the Choi representation. So this is essentially the Choi representation. And we can see that the complete positivity is actually equivalent to two facts. So the complete positivity and trace preserving. So completely positive implies that this is true. Okay, and actually this is an if and only if, and this is something that can be shown. So I'll write it like this. Okay, so this actually gives us a way to test. If somebody just gives you a mathematical description of a map and asks you whether this thing is completely positive, you can compute this object, you can compute the Choi representation, and find its eigenvalues. And if they're all non-negative, then you know that the map is completely positive. Okay, and then for trace preserving, this is true if and only if when we take the partial trace over B, then this gives us the identity. Okay, so these are two important facts. And because this object is normalized, we call it the Choi state. So I'll just so this is the Choi representation. Should have this here because it's normalized. Right, so these are two important facts related to quantum channels in terms of the choice state. Right. Now, because, one more thing I'll say about this. Okay, so one more thing is that because this gives us the action on an orthonormal basis of this channel, it can be used to actually describe the action. This Choi representation can actually be used to describe the action of any state. So we can write okay, so we can write it like this. Take another one. We can write it like this. Okay, so this here is the full transpose. So here we again have the transpose as we had last time. So as we described before. So this is just the transpose. All right, and this is something that can be shown straightforwardly using this. Okay. All right. So now that we have the basic mathematical description of a quantum channel, so the two important properties of a quantum channel are the complete positivity and the trace preserving. So what this tells us is that a quantum channel is some physical evolution that takes a quantum state and maps it to a quantum state. But not only does it do that, the complete positivity tells us that it also in some sense preserves the entanglement between two systems. And that even if you have if you have initially your system that's entangled with something that's inaccessible to you and you pass the channel through only the system that you have access to, even in that situation, the map will be positive. And that's also important from a physical point of view, because that's what you would want. You would want that if your system is entangled to something else, its property of being a state is preserved when you evolve it. It shouldn't matter if you don't have access to some other system that it's entangled to. Okay, so now let's look at some examples. So first example is what's called the depolarizing channel. Okay, so this is probably one of the simplest and easiest examples of a quantum channel to understand. And it's also very physically relevant as well. So it goes as follows. So okay, so this is what it looks like. And this is actually directly in this cross-representation form. Okay, and so P is a number between 0 and 1. So we can think of it as a probability. And these sigma x, sigma y, sigma z, maybe you have seen them before. They are the Pauli matrices. So it's that. And we can think of this as like a bit flip, in the sense that this is true. And then we have sigma z, which is this. And this we can think of as a phase flip, meaning that so we have this type of action in the standard basis. And then sigma y, this can be thought of as a combination of a bit and a phase flip. So you can show that it's actually equal, it's, I believe it is minus I sigma, yes, z sigma x. That's right. So we can think of the sigma y operator as being a combination of a bit and a phase flip. Okay, so what does this channel sort of describe? So it says that with probability p over 3, either the state gets applied, on the state there's applied a bit flip, a phase flip, or a combination of those, or with probability 1 minus p, nothing happens. So the state is preserved and nothing happens. Right? And another way of writing the action of this channel is maybe in a way that's more intuitive, or more easy to remember, which is the following way. So right? And the reason for this is the following fact. Okay, so the reason we can write the second equality up there is due to this identity. So is this. Okay, and this holds for any operator. So okay. And if we just use this fact, you plug it in and we work around with the expressions, and we'll get that. Okay, and so this has a nice interpretation in the sense that we can think of it as, with some probability, the state is completely preserved and nothing happens to it, or with 1 minus that probability, it is traced out and replaced with just a maximally mixed state. So it's a completely sort of garbage state, right? It's so from that state, you have basically no information. All information about your system has been lost. So it's kind of all or nothing situation. So either you get it perfectly or you don't get nothing, essentially. So that's what the depolarizing channel is. And this comes up in models of quantum computing, for example, where people will do sort of analysis of the noise on the quantum computer. They can essentially model it as this kind of noise on the gates acting on the quantum computer. All right. In order to show this, so it's relatively straightforward. So I'll sort of give you a partial sort of solution to figuring this out. So any operator rho can be written in the following way. So there's a general fact which tells us that, so here I said that this forms an operator basis. So this forms a basis for the space of linear operators. But also, is a basis for the operator space. So any matrix can be written, or any 2 by 2 matrix in this case, any 2 by 2 matrix can be written as a linear combination of these matrices. So So what this means is that we can write rho as in this way, where are real numbers. So these are real numbers. And they're real numbers in this case because we're assuming that rho is Hermitian. Okay, so if we just take this form, we plug it in, and we work around with it and use some of the properties of the Pauli matrices, in particular the fact that they anti-commute. So for example, sigma x. So for example, that's true, but they all mutually anti-commute. So if we use these types of properties and we work around with the expressions, then we'll get exactly this. And we note here that the trace is just alpha 0, just by looking at this. And the Pauli operators are traceless. So if you take the trace of any one of these, it's 0. And that follows immediately from this, because the diagonal elements they sum to 0. In 2 of the cases, they are always 0, and in 1 of the cases, they'll sum to 0. Okay, so that's the depolarizing channel. Okay, so let's look at another one, which is probably the most important for the case of quantum communication. And this is when this is the channel that's usually used to model fiber optic communications. So that was the first example. So here we have let me use a different. Okay. So we call this a pure loss channel, and it's a model for an optical channel. Okay, so in particular for sending like photons through a fiber optic cable, this is the model that is almost always used to describe what happens to a quantum state. And we can think about this in a nice way in using the following diagram. So we have some input state rho. And here we have what's called a beam splitter. So this is beam splitter. And then, so this is a beam splitter with the transmissivity or transmittance. So eta is a number between 0 and 1. And it essentially tells us whether or not a photon, when it impinges on this beam splitter, will either be transmitted or be reflected. So eta is the probability that a single photon passing through here will be transmitted through the beam splitter. And here, the environment, you imagine it to be actually described by an infinite dimensional Hilbert space, and this is the vacuum state of that infinite dimensional space. And that's essentially it. So this is, so we can describe this basically in the Schrodinger picture, exactly in that form. So we can say that where here this beam splitter described by unitary is described by unitary. So maybe you have seen this before. I'll write the unitary in a moment. So we get we get that. So this is exactly of that form. So we have the initial system coming in, It impinges on the beam splitter, and this is the interaction. This is the interaction part now between the system and the environment, is this beam splitter. And then what happens afterwards is described by this operator, but then because the environment is not accessible to us, we trace it out, and just to get what the state of the system is at the end. And this beam splitter is this is where can't exactly recall. It's like something like this, where these are the creation and annihilation operators for the system and the environment. Yeah. Okay, and there's a very important special case of this when we deal with qubits. So we can take an infinite dimensional Hilbert space and we can convert it into a qubit space. So if we can think in terms of like horizontal and vertical polarization. So and in this way, we get another example of an important quantum channel. So okay, so now let's look at a special case of this. Okay, so here let's look at right, so we say that when we put an H in a ket like this, it's a horizontally polarized photon, single photon. But we have two optical modes. So we can think about having two fibers, for example, or just two optical modes. Let's just say two optical modes. So M1, M2, and we put one photon in, for example, the second mode. And for a vertical, we put the photon in the first mode. Okay, so this basically describes a qubit for us. So this can be thought of as an encoding of a qubit into two modes, two optical modes. And so we often call this the dual rail encoding. All right, so we can take so whatever state that we want to send over this quantum channel, depending on what the state is, we have this sort of mapping. So we say that if it's horizontal, then we encode it in this way. If it's vertical, we encode it in this way, and then we can also do any superposition based on this. Then what happens when we send each one of these modes through that channel? So what happens in that case? So if you have any state rho on these two modes, but it's only spanned in this space given by these two states. So there's only ever one photon in the system, 1 or 0 in each of the modes. We send it, each one of these modes we send through the channel. So then what we get, and I don't have time to go through this right now, but what you get is this. Okay, so you get something that's very similar to what happens in the depolarizing channel, except it's in this form. So with probability eta, the state is traced out and replaced with just a vacuum. So it's both modes are in the 0 state. Or with probability 1 minus eta, the state is completely preserved. So this is also kind of like an all or nothing situation. So with probability 1 minus eta, your state is completely preserved with perfect fidelity. And with probability eta, it's completely gone and replaced by vacuum. Now, usually what happens in quantum communications is that this eta has a specific form. So it's usually something like e to the minus alpha L. Well, alpha is some parameter that characterizes the fiber optic cable or whatever the medium is that it's traveling through, and L is the length. Right, so basically this probability is very low. Yeah. I might have. I think it should be the other way. Yeah, I think it should be the other way. So sorry about that. So I think it should be like this. Yeah, because the probability that it's perfect should be decaying with distance. So it should be this way. Yeah. Sorry about that. Yeah. So it should be like that. Okay. So these are two examples of quantum channels that we can think about in terms of a physical sense. We also, as I mentioned before at the beginning, we can think of quantum channels as some kind of tool to do calculations. And so one of the examples that I'll show now is related to that. So last time we talked about measurements, and we talked about how measurements can be described using POVMs, which stand for positive operator valued measures. So let me recap that very briefly. So it turns out that when we measure a system, that can also be described by a quantum channel. So that can also be described by what is a CPTP map. So we can also describe it as a channel. Okay, so this is, I guess, the third. Is there any questions about any of this so far? Okay. All right. So measurement channel. So from last time, we saw that measurements can be described by operators of this form that satisfy these properties. Satisfy these properties. Okay? And we can think of, and then the measurement probabilities. The probability of getting X is that, when the state of your system is rho. So now we can think of this as a quantum channel as well. So we can say that we have a map, or we have a channel M, whose action on the state rho is of this form. Okay, so what we essentially do is we form a diagonal matrix where each of the elements of the diagonal matrix is just the probability of obtaining that particular outcome corresponding to that element. And we think of this as being we just think of it as being a classical register. It's a classical register that stores the outcome of the measurement. So it's very similar to the concept of the probe that we talked about yesterday. So it's just a classical register that stores the outcome, and here we have just the probabilities. Right? So now a special case of this. So there was a question about what the post-measurement state is when we do a measurement. And we can think about this in terms of what the post-measurement state is when we just measure one half of a system. So we can now imagine that we have a bipartite state, and we want to measure A only. So now we can take the formalism of the measurement channel and we can apply it to only the A system and see what happens. So here, A to X just means that we're taking the system A, we're measuring it, and then we're sort of evolving into this other classical register X that stores the outcome. And then you get this. So here, okay, so this is exactly analogous to this, except now what's happening is because we have two systems, we only trace out the one that we're measuring, and our register X is going to be in tensor product because there's still one other system left, which is the B system. All right, and we can now write this in a slightly different way. In this way. Okay, so all I did here was make the following definition. So this, where P of X is just the usual definition of probability based on the Born rule. Okay? So these are just the probabilities of the measurement outcomes. And here all I'm doing is I'm normalizing this operator so that it has trace 1, so that it really is a quantum state. So if you take the trace of this, we'll see that it's 1, because then the trace of this will be equal to P of X, and then it will cancel with this P of X, and we'll get 1. Okay, so we can think of this as being the post-measurement state on system B, conditioned on the outcome X for system A when they do their measurement. So this is for A. All right? And again, we can think of this register as storing the outcome of the measurement. Okay? And suppose that for some reason the outcome of the measurement was unknown to us, or if it was somehow lost. So then what would be the post-measurement state in that case? Right? Because then we don't have knowledge of what the state was. We only know that the state of Bob is this when we see that the outcome of the measurement is a particular value X. But if we don't look at the outcome of the measurement, or somehow we forget it, or it's lost, or it's just not accessible to us, then the way to describe the state after the measurement is going to be by tracing out the X register. Okay, so this is the post-measurement state. So if the measurement outcome is then it's going to be the partial trace of X of this state. So let me call the state this state, rho XB. Then I'm going to trace out. And if I do that, because this is already sort of diagonal when I trace it out, so we'll write it out. So this is just, which is 1. With the P. Okay, so in this case, if we don't know what the outcome of the measurement is, then our state of the system after the measurement has to be described by a mixture over all possibilities of the conditional states. Okay, so this is what we get. Yes. Yes. So here we're talking about just P. Yeah. Okay. So this is one element, and now, so this is something where we call it a quantum channel, but maybe it doesn't directly correspond to some physical evolution in the traditional sense, but mathematically speaking, it is a completely positive and trace-preserving map, so it's a channel. And it's useful because it allows us to describe calculations in a very neat sort of way, right? So, for example, here, the measurement outcome was unknown, so all we had to do was take the partial trace, right? So that makes it sort of a nice, neat mathematical description of what happens. All right. So one last example that I'll show before we move on to the main thing. Okay, so actually, there will be one more example before I do the thing I wanted, which is, I guess this was, yeah. Is a quantum instrument. All right. So last time we talked about what the post-measurement state of the system that we're actually measuring is. So if we have that as our POVM, then for the system, the post-measurement state is that. But sometimes we can think of a more general kind of map where the post-measurement state isn't just this, but rho x is instead some other action of under some other set of maps. Okay, so which are not necessarily trace preserving, but they are still completely positive. So this describes a situation in which we have a measurement, but we're maybe coarse graining the outcome. So depending on what the outcome is, maybe we have several outcomes and we want to lump them into one. So in that case, we would not describe it necessarily in this way, but it would just be some other general map. So these are, so they're CP maps such that the sum is trace preserving. So we can think of this map as having one Krauss operator, right? Because this is a Krauss, this itself is the Krauss operator, and it's only one Krauss operator. But you could have a more general scenario where the Krauss operators, there could be more than one Krauss operator. And so that's what this is describing. So it could be a situation where the map has maybe 2 Krauss operators or 3 or so on, right? And this set of maps, we call that a quantum instrument. So we call this a quantum instrument. Call it a quantum instrument. And the corresponding channel for that is, say, is like this. Okay, so this is very similar to what we have here, except we're now actually looking at the post-measurement state of the system that we're measuring. So here, this is again storing the outcome of the measurement, and here we're storing the post-measurement state. Right, and this is now going to come up in the next example of a channel that we look at. So here, this action of E on this state is also a channel. And these are, because of the fact that these are completely positive and their sum is trace preserving. So if we take the trace, then we'll get this kind of sum appearing, but then the sum is trace preserving, so the overall thing will be trace preserving. All right. So the final example of a quantum channel, that's probably the most important for quantum communication, in the sense that we use that as one of our tools. Is the LOCC channel. So LOCC stands for local operations and classical communication. All right, and so this is a general paradigm in which we have two parties. We have Alice and Bob. And basically what I described at the beginning, saying that the task of communicating essentially involves doing local operations, local encoding and decoding, and classical communication. Right, and so this is exactly what this is about. So we can sort of draw this in a nice way as follows. So say Alice and Bob start with some initial state. We have Alice at the top and Bob at the bottom. Alice does some local operation at her lab. And in general, this will be some quantum instrument. It's something that consists as an output of a quantum system with also a classical register. So here we see that the output of the system is a quantum, output of the channel is a quantum system, but also a classical system. So that's what's happening here as well. So we have A here, and here we have A hat, and here we have, say, X. Right, and it's a classical register, so we draw it with a double line. So here we have a boundary. So here's Alice. Here's Bob. So now this is the local operations part, and now we do the classical communication part. So the classical communication part is where we take this X, which is a classical register. So I'll put a sub A here, and that's the only line that crosses this boundary between Alice and Bob. So it's a classical communication channel. It could be like a phone call. It could be something that's just classical communication. So it's not a quantum channel. So it's a classical channel. And it goes through to Bob, who does some other locally, some channel. And the final state is that, omega. So here we have X, B, and here is B. And this is B hat. So overall, this is our LOCC channel, so I just call it L. It goes from A, B initially to A hat and B hat. So we can describe it as sort of a combination of three things. So the first was this part, where Alice did something locally in her lab. The second part is a classical communication channel from Alice to Bob. And the third part is the local operation on Bob's side. So we can describe it as in this way. And this is the classical communication channel. All right. So the most important example, or the most common example of an LOCC channel is essentially quantum teleportation. But probably, okay, so we'll have to save this, I guess, for next time, but I'll just briefly mention that an example of an LOCC channel is basically the first example of a communication protocol that we're going to see now, which is the teleportation protocol. Okay, so this is a protocol for quantum communication. With shared entanglement. Okay, so I'll quickly sketch this, but we'll go through the details next time. But let me just quickly sketch it. Okay, so we have, so we again have Alice and Bob. So now the goal in this is what? So the goal here is for Alice to transmit some quantum state from her lab to Bob's lab. Okay? So all right, and what are they given? So they're given a perfectly maximally entangled state shared between the two of them, between Alice and Bob. So where, let's recall that this, and this is the maximally entangled state. Okay, so this is a very interesting protocol in which they're actually not even connected by a quantum channel. So Alice and Bob are not connected by a quantum channel, but in place of the quantum channel, what we have is this shared maximally entangled state. All right? And without actually transmitting any quantum systems, Alice can transmit this state to Bob. So we'll go through the details next time, but let me just quickly sketch what this looks like. So here we have this. So here we have what's called a Bell measurement. Here we have A, we have B. All right, so this is essentially a sketch of the protocol. So at the first step, Alice takes the states that she wants to teleport, which is what we call it, to Bob, and she takes that qubit and the qubit that's entangled with Bob and does what's called a Bell measurement on them. So the Bell measurement is a measurement in which the POVM elements corresponding to the measurement are the 4 Bell states. And so the outcomes will consist of 2 bits, A and B. And those bits A and B are communicated to Bob. So this is exactly what's happening based on what we saw here. It's following the general scheme that we have here. So this part is corresponding to Alice's measurement. We have a corresponding classical communication. And then at Bob's end, what he's going to do is some local operation conditioned on the values that he gets from Alice. And what we'll show next time is that this actually works. So if we start with psi up here, then at the end of this protocol, psi is here at Bob. And this is without any transmission of actual quantum bits, just classical bits. And the cost of this is just to have this shared maximally entangled state, which effectively simulates an identity channel. So we go from here to here perfectly with no error. Okay, so that's it for today.
Any questions? Well, I will ask you to go back to the pure loss channel again.
Okay.
I understand it from the explanation of you're just having a probability of losing your system. But I was a little bit lost on this beam splitter way of seeing it. And
okay.
I would ask you to go back at this again.
I see. Okay, so I mean, in some sense, we can define the pure loss channel in this way. So the beam splitter is something that can be described in just in this way. So here, it's like, so we have a photon created in one mode and then lost in the other, or the other way around, right? So is the question why we can think of this eta as corresponding to losing a photon?
From the point of view of the beam splitter, what this parameter means?
So from the point of view of the beam splitter, so it corresponds to, so we can think of this as corresponding to some kind of reflectivity of, so if we have some material here, so physically, what is a beam splitter, right? So a beam splitter is just going to be some kind of mirror with some reflective coating on it. And the kind of reflective coating you have on it will dictate what this value is. And so with some probability, or with some fraction of the light, I should say, right? Physically, it will just be some fraction of light. You can shine a laser beam on it. This is not necessarily some quantum object, right? So this is the kind of thing that you have in your lab, and you can just shine a laser on it. And some fraction of the light will pass through, and some fraction will be reflected. And that fraction is given by this eta. And you can control this eta by taking different sort of refractive coatings or different thicknesses, things like that. And when we just take, when we shine only single photons, in that case, we'll get this behavior that one of the photons passes through with this probability, or with the other probability it goes to the environment. Yeah.
Thank you. Other questions?
Do you lose any generality by considering only one-way classical communication in this lock channel?
Yes. So yeah, that's a good point, actually. I should mention that this is actually just a one-way LLCC channel. So yeah, what I've drawn here is actually just a one-way. So yeah, it's not the most general thing. So the most general thing will be having, yeah, that's a good point. Thanks for bringing this up. So what I wrote here is actually just a one-way LLCC channel, because it involves only classical communication from Alice to Bob. But you can have the same thing going from Bob to Alice, and then you can have several concatenations of that. So you can have several back and forth rounds. And that gives you a general LLCC channel. So a general channel will be, so this is, yeah. So more general, LLCC channel will just be, say L1 going in this direction, in the other direction, and so on. So it'll just be back and forth, and several concatenations of this for some finite number of rounds. Yeah, thanks.
Any other question? If not, let's thank Sumit again. So tomorrow we will have the class at 3, and on Friday we will have 2 classes to compensate for the holidays on Thursday. Okay, one in the morning and one in the afternoon, the normal time.